move to the next speaker, Philippe Miele. He came from Montpellier. He, in fact, studied there in '93 chemistry. Then he moved to a postdoctoral stage to Georgia Institute of Technology at Atlanta. And then he returned to Montpellier, where he was assistant professor in '94 and the University of Lyon first, and then he moved to other institutions there, and since then he has been especially since 2010, he joined the European Institute of Membranes in Montpellier. His interest is mainly in boron chemistry. He has co-authored around 260 papers, 12 patents, 35 PhD theses. Recently, he was elected as the World Academy of Ceramics affiliated. He's going to talk about boron chemistry, boron nitride, as you can see in the title of his talk. So, Professor Miele.
Thank you very much for this very kind introduction. First of all, I would like to thank the organizer, particularly Clara and Eva, for this invitation to this very, very nice conference. I'm very happy to be there in this PBSI 2018, and also I'm very happy to be in Spain, particularly in Barcelona. I like very much the city. Let me say also that I'm really fascinated with the chemistry I saw till now, with this very beautiful boron clusters, cages, also the chemistry presented by Professor Tyler. Also, I'm really impressed. But since I'm not good enough chemist, I will only deal with two atoms, boron and nitrogen, and I will try to show you what we can do with this boron nitride to prepare materials, ceramic materials. This is our institute in Montpellier, European Institute of Membranes, in which we are working mainly in membranes, inorganic or polymer membranes. This is for application in energy, environment, health. And this is the city about 200 kilometers from the Spain border. And this is some views of the city and the seaside and the beach. And if you stay till my last slide, you will understand why I show you this. So the core of the talk today is boron nitride. Boron nitride is an artificial ceramic which is analog to carbon. Thus, it exists among two main polymers, the cubic boron nitride, which is analog to carbon diamond, and the hexagonal boron nitride, which is the most stable phase, analog to carbon graphite. And here you have the structure, a very simple structure. This is a layered structure with hexagon, B3 and 3 hexagon in the planes, in which the bonds are covalent, and these layers are linked through van der Waals interactions. This is very important for the second part of the talk today. And you see also that boron nitride displays a very unique set of properties, very specific properties. The lowest density of the ceramic materials, high tensile strength in the direction of the planes due to the covalent bond, particularly a good resistance toward oxidation above that of graphite, and chemical stability. And also this is a non-toxic materials. So you can see part of the applications, for example, part of aerospace vehicles, part of nuclear reactor. Here is a tokamak, crucible, and also for cosmetics, particularly high-quality cosmetics like Chanel, for example. They use a lot of boron nitride in their products. So this is the outline of the talk with two main parts. In the first part, I will try to show you how to prepare shaped ceramic with a chemical route. This route is called Polymer-Derived ceramics. And the second part will be dedicating to the use of nanosheets, BN nanosheets, to prepare specific materials with new properties. And the second goal of the talk also will be to show you how to generate, tailor, organize, maintain, and so on, a porosity leading to structured materials for specific application, particularly membranes, and by trying to develop simple, cheap, and sustainable synthetic method. So the first part is this polymer-derived ceramic routes, which is a chemical route starting from molecular precursors. This could be commercial or synthesized in the lab. Then it can be chemically modified in order to be reactive. These precursors are converted into a preceramic polymer, meaning that in this preceramic polymer you have the structure of the final ceramic. These polymers can be also modified, and they contain, as I said, all the elements of the final ceramic. They also display an ability to be shaped, and for this you can use methods derived from the plastic industry, for example. You prepare the shaped polymer by the, for example, spinning method or plastic shaping and so on. And after that, you have to treat your polymer at high temperature to convert them into an amorphous ceramic and finally a crystalline ceramic. So these ceramics at this stage can be also powders, and they can be shaped in another way after that. By this way, it's possible to produce non-oxide ceramics, particularly boron nitride. And the difficulty with this method is that you don't want to have any oxygen in this ceramic, and all of these precursors are sensitive to air and moisture. So starting from the room temperature to around 1,000 degrees, you have to work in a completely neutral or atmosphere, or for example in the atmosphere nitrogen on argon. Also, you have to keep in mind that from 20 or from let's say 0 degrees Celsius, you have to go at the end to 2,000 degrees for the complete transformation into the ceramic. Now, a few words about the precursors. The precursor for this BN are mostly based on borazine, which is the well-known analog of benzene, inorganic analog of benzene. The reason is this borazine display a B3N3 core, which is the same than in boron nitride. And you have to pay attention in the ceramic world to what is called the ceramic yield, meaning the weight of ceramic at the end of the process compared to the weight of the precursor. So this precursor display usually a high ceramic yield, but you will see that we have always to find a compromise between the ceramic yield and the processing properties. For example, the borazine here display a very high ceramic yield because you just need to remove 6 hydrogen atoms to reach the BN formula. But the polymer you can prepare from it display a very low processability. So you can use this precursor, which is a liquid vapor or liquid solid state process very easily, but not in molten state. If you take this kind of precursor, this is only an example in the family of alkyl aminoborazine. You have a polymer with a lower ceramic yield because you have introduced these monomethylamino groups, but you can prepare polymers with very good processability. So this will be always a game between these two parameters, and you can use this precursor in molten state or in solution, depending on if you use the monomer of the polymer. As an example, a relatively old example we have performed in the group for the preparation of boron fibers. You take this 3-methylaminoborazine, the precursor I just described here. It's relatively easy to polymerize, to thermally polymerize to obtain this kind of polymer with N-methyl bridges between the rings. And this polymer display good processing property because it can be, it is fusible at around 180 degrees, and you can melt sponge this polymer into this very nice polymer fiber with about 20 microns in diameters. You have the SEM picture. It's here the fiber is very, very smooth with no defect. After that, you have to convert your polymer into ceramic, so you have to remove the organic group, and for that you have to treat the polymer fiber under ammonia up to 1,000 degrees, and at the end, at this stage, you obtain an amorphous ceramic, and if you want a crystalline ceramic, you have to treat in a second step under nitrogen up to 1800 degrees to obtain these very nice BN fibers with 10 microns in diameter. You can see here that these fibers are very nice. They are polycrystalline, and they display tensile strength up to 2 GPa with a very good Young modulus also. And just for details, these materials have been developed for composite materials for aerospace application, specific part of aerospace application. So if I come back now to, if I go now to other example, the porous material example, particularly the mesoporous materials, they display a high specific surface area, a narrow pore size distribution. The pores have dimension from 2 to 50 nanometers. And if you want to prepare these materials, for example, in the silica system, it's relatively easy to do that using a soft template route in solution by self-assembly. But if you want to prepare the same materials, the same kind of materials in the non-oxide system, it's very difficult. And the only method is the hard templating method, which is a long method with several steps. You take a template, you infiltrate the precursor in the template. After that, you convert your precursor into polymer or into a ceramic. And at the end, you have to remove the template to obtain the replica of the starting structure, which is a very long process. Anyway, we've done that for BN and other systems, starting from, for example, silica template SBA15 or carbon template CMK3. Here, this is the example with CMK3 as template. We did that with the methyl aminoresin, the precursor I showed you at the beginning. We treat this with under nitrogen up to 1,000 degrees to obtain a composite carbon boron nitride, and at the end you have to remove the carbon by a reductive treatment under ammonia up to 1,000 degrees to obtain the replica structure of the starting compound. This is the idea, and here you can see the result. At the beginning here, the nitrogen absorption analysis, which shows the mesoporous character of the ceramic, of the BN, and here's the small angle X-ray diffraction data showing the organization of the porosity. Here it's for the carbon, here it's for the BN in the powder, and this has been confirmed by the TEM images. Here's the carbon with you can see the hexagonal organization of the porosity. And here is the boron nitride with some organization also of the porosity. And this structure is a replica of this structure. So we have shown that the ordering of the porous structure provided by the carbon template is maintained. And you can see also that the centers of the channel are distant of about 7 nanometers, which is in agreement with the X-ray diffraction data. And that shows the efficiency of the template elimination process for the retention of porous structure. So now if I change of precursor, going to borazine, this precursor can be polymerized very easily at low temperature from around 40, 50 or 60 degrees. This is a liquid. And you can obtain this polyborazylene with direct BN bond between the borazine rings, explaining the low processability of these polymers anyway, but this is another story. And by pyrolysis under nitrogen up to 1000 degrees, you obtain this amorphous BN ceramic, which can be crystallized at higher temperature up to, let's say, above 1500 degrees to obtain this a very crystallized structure, as depicted here by the X-ray data. This is the X-ray data of the BN heat treated at 1800, showing the very good crystallinity of the materials. Coming back to the ceramic yield, you can see by this TGA analysis also that the ceramic yield is above 95%, which is very, very high, as I said at the beginning of the talk. Using this precursor, it's possible to prepare a lot of structures that we have done in the group: coatings, membranes, composites materials, zeolite-like porous materials, compact monoliths, dense monolith, and so on. And also, I will just focus on this particular porous materials today, starting from borazine, which can be polymerized at 50 degrees. We obtain this polyborazine, and by impregnation, the method is relatively easy, but the same that I had already described. You can prepare this kind of porous structure, and particularly this very nice structure with a hierarchical BN monolith, meaning that the porosity in these monoliths is hierarchical, starting from micro to macro porosity. And this has been done starting from this carbonaceous foam, which has been impregnated by this polyborazine, as I said. Here you have the nitrogen adsorption-desorption analysis showing the mesoporous character, and also that we have 25% of microporosity inside. These structures are very resistant to mercury porosimetry, meaning showing the mechanical robustness, and the porosity is very high, 80% in average for these two structures prepared at these two temperatures. So now I'm going to skip to the nanomaterials part of the talk. Just few properties of these BN nanomaterials, meaning BN used directly. This is very interesting for thermal management, lubrication, nanoelectronics, and particularly a new application of BN is the osmotic power harvesting, which is very important now. These very nice papers shows the potential of these materials for the osmotic power harvesting, and also as BN and nanoporous membranes. I will just show you today two examples of what we've done in the group based on BN for dense membranes for gas separation, and also a very new study for polymer membranes for water purification. The idea is to use 2D boron nitride particles to inserted in this system to prepare new materials. This is very simple, contrary to the previous part, in which the chemistry was much more difficult to perform. So the first idea is to prepare this boron nitride nanosheets. You can see that these BN nanosheets can be called also a graphene-like BN because the structure is almost the same. You have the graphene here and the graphene oxide here, and it's relatively easy to obtain, starting from a gelatin solution with a BN powder, a commercial BN powder, and after an ultrasonication, you obtain a solution, a stable dispersion of boron nitride into the gelatin, and this can be used directly to prepare, for example, films and after that, membranes. So this is a characterization of the nanosheets. You can see here the X-ray diffraction data showing the very good crystallinity of the boron nitride particles we have used. This is the SEM picture. Here the Raman spectra, which is perfectly in line with the data of BN, and with this AFM image, we can deduce that BN display 1.5 nanometer in thickness, with a lateral size of approximately 0.5 and 1 micron, showing the very good, very efficient exfoliation of this boron nitride nanosheets with this very simple method. After casting of this dispersion, BN in gelatin, you can obtain this kind of membrane with two scale. And this is very interesting. This is the X-ray diffraction data, which are very interesting. For the gelatin alone, it's the black line with no diffraction. For the red one is the BN itself, so you can see the characteristic peak of BN for the 002 and 10 signals here. And if you look at to this blue spectra, you can see that these signals have disappeared, showing that you have preferred alignment of the BN in the structure parallel to the plane. The result, here you have the picture of the membrane, and this is the result of the permeability of oxygen through this membrane. I will not comment this mechanical property because I have no time to do that. And you can see that the permeability decreased to 0.05 barrier. Barrier is a unit, specific unit for this kind of permeability at 2 bar, and thus we have an enhancement of the barrier properties by a factor 500 at 2 bars, which is very, very good, for example, from food application, food packaging. So this is related to the good dissipation of the graphene-like BN in the gelatin matrix, which has been showed by XRD and EDX, the alignment of the graphene-like BN along the film, as it is shown here, and also the good interaction between the gelatin and the graphene-like BN inside the membrane. So the last example for today is a very, very new study that we have started in the group with a PhD. The idea is to use Pickering emulsions to prepare porous materials. Pickering emulsions are colloidal suspension stabilized by nanoparticles instead of organic surfactants, and these particles are localized at the interface between the two phases. This has been discovered at the beginning of the 20th century by, this has been observed by Ramsden and discovered by Pickering a few years later. And the idea and the interest of this emulsion is that the particles are completely sticked and at the interface, and the meaning that you can obtain a very stable emulsion. So two kinds of emulsion exist: oil in water, meaning oil drop in water, and water in oil. So water in oil emulsion are the more stable against collapsing, and the interest of the 2D materials as stabilizer are the large reduction of the free energy at the liquid-liquid interface, providing a very good stability of the system. So we have worked on graphene oxide and particularly BN. The interest of this method is high atom efficiency, the multi-layers tiling, which is possible with flat particles, the barrier properties at the interface, and also the templating for the creation of new material structure. So this has been done very easily. The first part, you take water, you put BN, boron nitride, commercial boron nitride inside the water. You sonicate this to exfoliate the BN inside the solution. You add oil to this system, and after that you sonicate another time, and you obtain this kind of dispersion in which the dispersed phase is the water inside the droplets, and the continuous phase is the oil. In our case, the oil phase is ethyl benzoate, and the exfoliation of HBN led to this very small particles with 2 to 6 nanometer in width and a lateral size in the range 10 to 150 nanometers, which is evidence of very good BN exfoliation, which has been shown by AFM. This has been published in Langmuir very recently. Now the photographs of the emulsion. You have all this system with a different quantity of different ratio of BN, and you can see that the size of the droplets depends on the concentration of BN inside the emulsion. The highest concentration of BN led to the smaller droplet size, and for 2% of BN, the droplet size is around 6 micrometer. And if you use a lower oil, or a low oil on water ratio, for example, lower to 0.6, you have no emulsion formation. So this has been done by optical microscopy, and if you want to characterize the two phase, it's very easy to use this epifluorescence microscopy, and this with a fluorescein sodium salt, which is soluble in the water, and by this way you can see, because the droplets are very fluorescent, you can characterize, you have a water in oil emulsion at this stage. If you use a differential interface contrast technique, you can also show that you have a very good contrast between the two phases, and also that you have a high contrast at the interface, showing that you have a lot of all the BN at the interface of the droplet. And these are some images showing the stability of the emulsion. For example, 14 days after the preparation, the emulsion are still stable. Now the idea was to use this emulsion to prepare materials, for example. So there are several applications as drug delivery system or bioimaging agent, but our focus is on material templating. And it's possible to prepare microspheres, for example, or forms. This is in progress with another system and other techniques in the group. And the first example we've performed is the preparation of membranes directly by using these emulsions. If you look at this scheme, you can see what is possible to do with these emulsions. If you polymerize both phase, you obtain a composite. If you polymerize only the dispersed phase, you can obtain a polymer latex. And if you polymerize the continuous phase, you obtain a porous materials. This is quite evident, as this has been done in these two examples, for example. And in our case, we have used polyvinyl alcohol to prepare membranes, because it is biodegradable, it displays hydrophilic behavior, good mechanical properties, and also particularly is non-toxic and harmless. So it's good candidate for the development of membranes with anti-fouling properties. The idea is to use these membranes for the water purification. So the technique is very relatively easy also. The first step is the same. You put BN inside a water phase. You sonicate to exfoliate the sheets. After that, you add the polyvinyl alcohol. You heat that at 80 degrees. And at the end, the ethyl benzoate with a last sonication, to obtain this kind of emulsion with, in that case, water as a continuous phase and oil in the dispersed phase. This emulsion can be used for the membrane preparation with a technique very spread for the preparation of polymer membranes. So you cast the emulsion on a glass support. The emulsion contains boron, nitride, and PVA. You obtain the membrane, and you let the membrane for what is called a curing, meaning that you let the solvent, water and ethyl benzoate to evaporate. And after that, you have to provide good mechanical properties to the membrane. So you have to cross-link the membrane using glutaraldehyde in ethanol with hydrochloric acid. So here are the membranes with the PVA membranes alone with no porosity. The PVA prepared after a curing time of 24 hours, and these two membranes with a curing time of 3 hours or 1 hour. So, as I said, the curing time is necessary to remove the water and oil, and this method can be used to tailor the porosity of the membranes. Now, the test of permeability and also of the rejection in order to characterize the pore size of the membrane. If you take this membrane prepared after a curing time of 1 hour, the mean pore size is around 1 micrometer. The water permeability is very high, 2,000 liters per hour, square meter, and per bar. And you can see that the rejection of the latex is very good for particles with 3 micrometers in diameter. And if you take this membrane after a curing time of 3 hours, you can obtain this very nice membrane also with a pore size of 0.2 micrometers and a water permeability which has decreased largely about 90 liters per hour per square meter and per bar. But in that case, the rejection of smaller latex particle is better, around 1 micrometers. You can reject almost 100% of the particle. Finally, this is the end of the talk. I would like to thank all the permanent staff which has worked on this different subject, and particularly the students, and particularly the last students, Danae Gonzalez-Ortiz, who started the study on this Pickering emulsion in the group. She's a very brilliant student because she's coming from Spain, but not from Barcelona. She comes from Valencia, but she did a very, very great job. I would like also to thank you, and before finishing, I would like to remind you that the next Boron meeting will be held in Montpellier next year in June, at the end of June. So it's time to register, it's time to send the abstract. And particularly, I've been told that we will have the World Soccer competition for women at the same time with a lot of games in Montpellier, so maybe the hotel will be difficult to book. So please, if you want to attend, don't hesitate to book right now. So we will be happy to welcome you, and I thank you very much for this, for your kind attention. Thank you.
You know? Okay.
Yes, I'm wondering if with the exfoliation technique you could maybe make a material that has alternating hexagonal BN, graphene.
This is a good question and good idea. We did that only for BN, but it's very difficult to combine the two materials because the structure are similar but are not the same. In BN, you have one boron atom above and below a nitrogen atom for the combination of the orbitals. But in graphite, atoms are shifted, and I think it's difficult to combine the materials in different sheets. But in the same sheets, maybe there is something to do to replace, as it has been shown the first day, some BN fragments by C fragments using the isolable system. Maybe it's a way to...
Yeah, I was thinking if you could, then that might introduce a band gap into the graphene.
Yeah, it's a good idea.
Which otherwise doesn't.
Yeah, it's a good idea.
More questions?
Congratulations, first of all, for the talk. Very nice and interesting materials. My curiosity was related to the mesoporous powders. Did you notice a variation? I don't know if you started the preparation from different types of precursors.
Yes, we did.
So did you notice a difference in the surface areas if you change the starting material to prepare them? Is there a difference?
No, it's not directly linked, because specific surface area is related to the feeling of the porosity, and the ceramic yield is impacted, but not the porosity. But the difficulty with the porosity is to maintain the mesoporosity at high temperature, because if you want to prepare boron nitride, you need crystalline. You need to go up to 1500 degrees. And at this temperature, usually the porosity collapses, so it's very difficult to combine the two systems.
And just one more, if I can. Have you ever tried to perform a gas storage measurements in these materials?
Yes, we worked with Professor Domirci with hydrogen storage, but in this kind of structure it's not suitable, because the mesoporosity is too big to store these small gases. But it can be combined with other systems. With a chemical storage, for example.
Or have you tried carbon dioxide?
No.
No. Right.
No.
Okay. Thanks.
There's time for more questions? No? Okay, if that is not the case, let's thank again not only Professor Miele but also Tile for the nice talks.